Imagine a massive vault swinging open to protect a single penny. That's what happens when using a frontier AI model for trivial tasks. In production, your API endpoint treats every user the same. One might ask for 2 plus 2, while another asks you to find the bug in this recursive async Rust function. If you route both to a model like GPT-4o, you're paying $15 per million tokens to solve basic arithmetic. But send everything to a free local model to save money, and your complex coding answers fail, leading to user churn. Treating these vastly different queries the same way creates a permanent trade-off between your API budget and your product quality. The common fix is writing hard-coded if-else rules to sort prompts by keywords. This approach is brittle because you can't predict every way a user might phrase a request. One unhandled edge case and the logic breaks. You could try fine-tuning a machine learning classifier to categorize every incoming prompt in advance. But that requires a massive pre-labeled dataset and constant offline retraining as your user's behavior changes. The problem is that you don't know if a model will succeed until it actually tries. This means routing is a sequential process. You have to make a choice, observe the result, and use that feedback to inform the very next request. This is the multi-armed Bandit problem. It's a framework for choosing between several options when the potential rewards are unknown. You have to balance exploiting an expensive, proven model against exploring a cheaper option that might be just as effective. The NeuralUCB Router is an OpenAI-compatible proxy that applies this math to LLM selection. When a prompt hits the proxy, it analyzes 15 distinct context features, like token length and task type, to create a baseline prediction of which model will work best. Because the system learns from the results of each live request, it builds its own training data without needing a human to label anything. The key to this learning is a mechanism called the upper confidence bound, or UCB. If a cheap model hasn't been tested much, the algorithm gives it a temporary uncertainty bonus. This bonus raises the model's total score, which directs the router to test that cheap model on a complex task. The router then evaluates the response quality and divides it by the token cost to calculate a reward. If the cheap model fails, the uncertainty bonus disappears. Its overall score drops, and it's bypassed for similar tasks in the future. If it succeeds, the baseline prediction rises. The router has now confirmed a cheaper path for that specific type of query. The algorithm learns quickly, reaching convergence after about 500 requests. At this stage, you'll see 80% of your traffic diverting away from expensive providers toward cheaper local models. This shift results in an 88% reduction in API costs compared to using GPT-4o exclusively. Despite the lower cost, the system retains 92% of the original response quality. The router acts as a filter. Complex reasoning tasks get the premium compute they require, while simpler chat and arithmetic are handled by low-cost alternatives. We are now seeing a massive shift away from relying on a single, massive model for every single task. Efficiency now comes from intelligent orchestration, building systems that can leverage a diverse network of specialized models. You can deploy this proxy today by visiting the NeuralUCB Router repository on GitHub to start optimizing your own API usage.